This is a quick review of Chapter 4 in Statistics. It describes a relation between two variables. First, some definitions. Bivariate data is new for this chapter. That means there are two variables being measured for each individual. Before, we just had lots of individuals with one variable. So now there's two variables that could be how height and weight compare to each other, or calories consumed and how much weight you lose, or how many hours you spend studying, what grade you get. It's two variables which you're wondering, do they have a relationship one to the other, or are they both just independent? The response variable is the variable whose value can be explained by the explanatory or predictor variable. And on a scatter diagram, it's like a scatter plot, you would put the explanatory variable on the x-axis, the response variable on the y-axis. So if you think one causes the other, the cause would be on the x-axis, the effect would be on the y-axis. There is a positive association in general when one variable increases, so does the other. And for a negative association, that means that in general, as one variable increases, the other variable will decrease. The main thing for this chapter is computing and understanding the linear correlation coefficient, which also is known as the Pearson produce moment correlation coefficient. Probably don't need to know that. What the correlation coefficient does is it measures the strength and direction of a linear relationship. Now, if you're going in a circle or a weird curve, this isn't going to be super useful. If you're taking the sample, and not the population, but the sample, so we're dividing by n-1, not n, and we're using sample, mean, sample, standard deviation, all that stuff, then the equation is as shown. R is equal to, on top, you take the sum of, for each data point, you take the x value minus the x bar average over the SX, the standard deviation, and multiply that by the y bar, or the y value minus the y bar average divided by the standard deviation for y. And you do that for all the points. See, that's your the deviation both in the x and the y for each point, multiply together, sum all of those up, divide by n-1, that is your R. Check your calculator to see if it gives you R or R squared, so you know for sure which to look for. All right, properties of linear correlation coefficient. First of all, it has to be between -1 and 1 inclusive. The closer it is to either of those extremes, the better relationship it is. If R is near +1, or if it's exactly +1, then it's a perfect positive linear relation, which would look like a straight line. The dots would all be perfectly in line with each other of your data points. If R is -1, then it's also perfect, but it's a perfect negative linear relation. Again, it would be in a straight line. All the dots would line up of your data points, and it would be sloping downward. As you can see in the two graphs, sloping up is the first one, sloping down is the second one. The closer you get to +1, the more evidence there is of positive association, and the closer those dots come to making a straight line. The closer you get to -1, the more evidence there is of a negative association, and the closer those dots come to making a straight line. If R is close to 0, then there is very little evidence of any linear relationship. There could be a different kind of curve involved, but not a linear one. R, the linear correlation coefficient, has no units, so it doesn't matter what your units of x and y are. They're not going to affect the value of R. And R is not resistant, which means it could and probably will be affected by outliers or any unusual data points. The least squares regression criterion is picking a regression line that minimizes the sum of the squares of the errors or residuals. So first of all, the residual is just, you can think of it as the error. It's what is the actual value of y minus what would be predicted by your regression line. So it's observed y minus predicted y. And then the least squares regression line, of all the lines you could possibly make up to try to represent to your data, the least squares regression line is the one that minimizes the sum of the squared residuals, or the sum of the squared errors, which means for every data point you go in there, figure out what the residual would be if you had that line, square that residual, add them all together, and the line you pick is the one with the least regression. The equation is, as you see, y hat is equal to b1x plus b0. And you can see how this reminds you of y equals mx plus b. Slope is the term with x. Y-intercept is the term without x. And to calculate b1 and b0, I put those underneath the main equation. b1 is r times sy over sx. S is your standard deviation, not variance, that's squared, but standard deviation is the sample standard deviation. And b0 is y bar, which is your sample y average, minus b1 times x bar, your sample x average. All those are x bar, again, sample mean, y bar, sample mean, sx standard deviation, sy standard deviation. And make sure you know that. Make sure you know these equations for your test. Interpreting the slope of the regression line is pretty easy. It's just like slope of a regular line. It means that if x changes by 1, then on average, y will change by whatever the value of the slope is, whether that's positive or negative. Interpreting the y-intercept is very similar to doing it with a standard y equals mx plus b line. It's the value of y when x is 0, but you need to ask yourself, is 0 a reasonable value for x? If it's not, then there's no reason interpreting this y-intercept that would be unreasonable. The other thing you need to ask yourself is, are there observations near x equals 0 in my data set? If there's not, then even if the y-intercept interpretation would be reasonable, it's still outside the scope of the model because you don't have enough data near there to know if the model is still reliable at that point. And finally, the coefficient of determination. This measures the proportion of the total variation in the response variable, remember that's the y-axis, that is explained by the least squares regression line. And there's a lot in your book about the total variation and the explained variation and all that. And at the end, the point you need to know is that r squared, which is capital R squared, is just the same as little r squared. I don't know why they changed it, but they do. So if you are looking for capital R squared, and in your calculator you have a lowercase r, just take that and square it. Or if you have a lowercase r squared, just that is your answer. That is your coefficient of determination, and it explains how much of the variation you see in variable can be explained by the line you just came up with your regression. That's it. Good luck.